So a T-beam problem. A T-beam slab floor of an office building comprises of slab of 150 mm thick, spanning between the ribs, that is beams, spaced at 3 meter center to center distance. The effective span of the beam is 8 meter, and the live load on the floor, that is they have given the load on the slab is 4 kilonewton per meter square, and they have asked us to use M20 and FE415. So generally we will write the given data, that is first given data is they have given the depth of the, that is slab thickness, that is nothing but the depth of the flange, df is 150 mm, and they have given that the beam is spaced at a distance of, that is spacing between beam is 3 meter, beam equal to 3 meter, and the effective span, that is L effective is 8 meter, and they have given the live load on floor, that is live load on slab is 4 kilonewton per meter square, and they have given the grade of concrete is M20 and steel is Fe415. So while you are solving a flanged beam, always try to draw the diagram. So first we need to draw the T-beam diagram. So they have given the depth of the flange as 150 mm, and I don't know the depth of the beam, so I am simply drawing a certain depth. So here that this depth is nothing but it is 150 mm, and they have given the slab, that is beam to beam distance. So let us consider this two are the beam, and the distance between these two beam is 3 meter. So as we know that half of the load will, when the load acting on this particular span, that is this particular region, the half of the load in this region will come to this beam, and half of the load will come to this beam, and also in this side also half of the load will come to this beam, and half of the load from this side will come to this beam. That means if we are considering this region, so here half of the load, the distance between the beam is 3 meter, so half is 1.5. Here also the half distance is 1.5. So I can write the load on beam, that is load on beam equal to load on the slab, into the spacing. Because why I am writing directly spacing between beam is, as I have already told that half of the distance from one side and half of the distance from other side. So if we add it together, then it will be the spacing between the beams. So load on beam is 4 and the spacing between the beam is 3. So that load on the beam is 12 kilonewton per meter, because we always know that the load on the beam will be the per meter, that is unit length load we need to calculate. So this is the value. So next, as usual, the main step is we need to calculate the dimension of the slab. That will be our first step in solving the problem. So dimension of beam. So here we know that we have the length and we know the effective length, that is effective length is nothing but L effective equal to 8 meter, and we know that we can calculate the effective depth of the beam by using the concept which was given in IS 456 page number 37. That is the, if it is L effective to the depth ratio, then if it is a cantilever beam, then we need to take it as 7. If it is a simply supported beam, then the L by D ratio is 20, and continuous, then the L by D ratio is 26. In this problem they haven't given any condition, so we are simply assuming that the beam is simply supported. So I am considering my beam is simply supported beam, so I am directly taking it as simply supported. So I need to use the term L effective, that is effective depth, L effective divided by D is 20 as per IS 456 page number 37. So I am taking this value. So if you look at the, if you come to page number 39 in IS 456, they have given a chart, that is the reduction factor for ratios of span to effective depth for flanged beam. So we need to consider this reduction factor while solving L by D ratio. So here they are finding this reduction factor based on the ratio of web width to the flange width. So first we need to know the what is the web width of the beam. So we are going to assume the web width and we are going to calculate the value. So the web width will be considered as BF, which will be the spacing between the beams, that is projection on either side. So I am just considering it as 3 meter for my calculation purpose, and I need to calculate the BW, that is I am going to assume it as 300 mm for my calculation purpose. So if I am going to calculate the web width divided by flange width ratio, that is 300 divided by 3000, because 3 in terms of meters, so when you are converting into mm it will be 3000, so the value will be 0.1. So as per page number 39 of this chart, if you are considering the value, that is flange width ratio, that is web width to flange width, if it is 0.1 it will come around at this point. So if I am going to project it, see here it will only starts at 0.8, so I can directly take the reduction factor as 0.8. so this will be in page number 39, and I am going to consider this L effective divided by, so here the reduction factor I need to write, reduction factor from figure 6 of IS 456 is equal to 0.8. So L effective by D equal to 20 into 0.8. So it will be 16. So I need to calculate the value of D. So if you calculate the value of D, then we will get it as 8000, because L effective which was given in our problem is 8 meter. So 8000 divided by 16. So the depth of the beam will be, we will have it as 500 mm. So here the value will be 500 mm. So I am going to consider cover of 25 mm. So I am going to have the overall depth D as 525 mm. So here if you look at this, we have calculated the value of BF, we have assumed the value of BF, and we have calculated the value of B width, that is web width as 300 mm, and we have calculated the effective depth which is 500 mm, and the overall depth as 525 mm. So next, as usual, we need to calculate the load. So the second step in our problem is load calculation. So load calculation. So here if you see, we have already calculated the live load on the beam is 12 kilonewton per meter. So we need to calculate the dead load of the beam, and we also need to consider this dead load of this web also in our problem. So we need to calculate the dead load, that is self weight of beam and self weight of slab. So first I am going to calculate the self weight of beam. So if you are considering the self weight of beam, then as usual I have considered, that is I have assumed that the overall depth of my beam is 550 mm, 525 mm, and that is the overall depth. Here if you see, I have calculated as 525 mm, and if you see the depth of flange is 150 mm. This overall depth is 525 mm. So I need, if I am going to consider only the beam, then I need to consider only this portion, because while calculating the slab, I am going to consider this total area for my self weight. So I need to consider only this rectangular portion. So here if I am going to calculate the depth of the beam, then the depth will be 525 minus 150, which will be 375 mm. So I am considering a unit length, and depth is 0.375, and the width of the web is, as I already considered, it is 0.3, and the unit weight of concrete is 25. So the value is 2.8125 kilonewton per meter. Then I need to calculate the self weight of slab. So as we have already calculated the self weight of slab, that is we know the thickness of the slab is 150 mm, 0.15, and the length of the slab, which is going to be the spacing between the beam. So the spacing between the beam is 3 meter. So I am considering this as 1 into 0.15 into 3 into 25. So if I am going to calculate this, then the value will be 11.25 kilonewton per meter, and I know the self weight, that is live load. Live load is, as I have already calculated in the previous step, that is load on the beam is 12 kilonewton per meter, and I am going to consider the floor finish load of 1 kilonewton per meter. Floor finish equal to 1 kilonewton per meter. So if we are going to calculate the overall load, then this overall load will be is 27.06 kilonewton per meter. So this will be my service load. If I am going to calculate my ultimate load, then I need to multiply this load with the partial safety factor 1.5. So if I am going to multiply this, then the value which I am going to is 40.6 kilonewton per meter. So I have calculated the value. Next we need to calculate the effective width of the flange, because in previous step we have only assumed the value as 3000 mm. So I am going to calculate the effective width of flange, that is BF. So in this problem, the only step, the additional step which we are going to do is the effective width of flange calculation. As I have already told you, from code book we are going to calculate this effective width of the flange. So if you look at page number 37 in IS 456, we will have a formula to calculate the effective width of flange for T-beams, which is equal to BF equal to L0 by 6 plus BW plus 6DF. So what I am going to do is I am going to calculate the effective width BF equal to L0 divided by 6 plus BW plus 6DF. So as I already told you, see if it is a simply supported beam, then the L0 will be equal to L effective. So simply supported condition, since simply supported, L0 equal to L effective. So what I am going to do, I am going to directly take 8000 divided by 6 plus the width of the web, we have assumed it as 300 mm. So I am directly taking as 300 mm plus 6 into 150. So if I am going to calculate this value, then I am getting the effective width as 2533 mm. And also if you look at the code book, we will have the another conditions, that is, but in no case, because this is the condition. If you look at our code book, it will have a condition, the L effective, that is B effective, sorry, not L effective, it is B effective. Width of the flange in no case can be greater than the breadth of the web plus half the sum of clear distance between the beams. To the adjacent beam means between the beams. So here this condition B effective equal to BW plus half of the distance, sorry. So here if you see B effective, that is flange effective flange width equal to BW, that is which was given our condition, B breadth of the web plus half the sum of clear distance, half into distance between beams. So here the distance between the beam is 3 meter, here it is 300 mm, that is width is 300, half into 3000. So here if you see, we will have the value 3000 plus distance to the adjacent beams on either side. So 3000. So here we are going to calculate. So half into, because it is a center to center distance, so we are directly taking it as 3000. So here the value will be, if you are using this, we will have it as 1800 mm. So as our code book states that the B effective cannot be greater than this value, because by using the formula we are getting it as 2533 mm, but as per the condition it should not exceed 1800 mm. So I am going to consider the B effective, that is therefore the effective width of the flange is 1800 mm. So next step, this is the additional step which we are using in this problem of flanged beam. Next step is we need to calculate the, as usual, next step is we need to calculate the bending moment and shear force. So bending moment and shear force. So since it is a simply supported beam, we know that the formula to calculate the bending moment is WL square by 8. So MU equal to WU L square, L, that is L effective square divided by 8, and VU equal to WU L effective divided by 2. So by substituting the value of W as 40.6 and L effective as 8, we are getting the value as 324.8 kilonewton meter. Next we need to calculate the VU value. So the value is 162.4 kilonewton. Next we need to, while designing the beam, we need to check where the neutral axis is going to lie. So in order to do that, we are going to do a step called as, we are going to calculate the neutral axis depth, that is neutral axis in flange. We are going to assume that it is going to be at the where it is going to locate. So here what we are going to do is I am going to consider the condition that is XU equal to DF, that is neutral axis is going to lie at the edge of the beam. So if you are considering this beam, then I am saying that the neutral axis is going to lie at this point. So we know that when the neutral axis is within the flange, then we can simply design our beam as a normal rectangular beam. But here I am saying that the beam is going, that is the neutral axis is going to lie between the web and the flange. So which overcome or which overrule that condition, that is neutral axis is within the flange. So we are going to check where the neutral axis is going to lie. So for that we are assuming this condition. So if you look at this, we are going to consider that condition, that is XU by D, that is XU is equal to the limiting value. That is I am saying that the XU value which is going to be as the flange depth. So I am going to use this formula to calculate the limiting moment. So MU equal to, because we are going to use this condition to check where the neutral axis is going to lie. So MU equal to 0.36 XU max divided by D into 1 minus 0.42 XU max by D into FCK BD square. So I need to calculate the value of XU max. So I have given that XU will be equal to DF. So the value of XU max will also be, that is I am considering XU is DF. So the XU max will be 150 because XU will be equal to XU max as per this particular condition. So if I am going to substitute the value 0.36 into XU max is 150, that is DF is 150 divided by effective depth is, as per our condition, it is 500 mm, and 1 minus 0.42 150 divided by 500 into FCK is 20, and B is, we are going to consider the what is the overall width of flange. So the overall width of the flange as per the condition is, which we have calculated, is 1800 mm. So 1800 into the depth is 500, that is 500 square. So this moment which we are going to find out will be the limiting moment. So if you solve it, the limiting moment which I am getting is 849.5 kilonewton meter. So this can be called as limiting moment. So this MU limit is greater than the MU which we have calculated. So if you arrive at this condition, then we can state that, therefore I can say that the XU, that is neutral axis, lies within flange. So this condition states that, that is, sir, when the limiting moment, that is when I am considering the flange, that is, so when the limiting moment is, when the neutral axis lies at the edge of the flange, then the maximum moment which I am getting is 849. So if it is going to be less than that, then the flange, then the moment value is going to be lesser. When the flange values, that is when the XU is greater than the depth of the flange, if it is going to be lie at this point, then the MU will be greater than MU limit. But here if you see, the MU limit is greater than MU, which suggests that the neutral axis is going to lie within the flange. So when the neutral axis lie within the flange, then the beam need to be designed as a simple rectangular beam. So we are going to use the same formula to calculate the moment which we have used in our previous problems, that is, so since the neutral axis within the flanged beam can be designed as a normal rectangular beam. So I am going to use this normal formula which we have used in our previous problem, and by substituting that I am getting the value as AST equal to 3855.4 mm square. So here I am going to use 20 mm dia bar, that is, sorry, now instead of 20 I am going to use 25 mm dia bar, and I am going to calculate the number of bars, because we know that if the area is small, that is if the size is small, then we need to calculate the number of bar. So number of bar equal to, we know the formula, total area divided by area of one bar. So here if you see, the total area is 3855.4 and the area of one bar is pi into 25 square divided by 4. The value which I am getting is 7.85, so which will be equal to 8. So here I am going to use 8 number of 25 mm dia bar as main reinforcement. Next I need to calculate the or check the shear, check for shear. So we know that we need to calculate the nominal shear stress. So as you all know, I am going to simply solve it and show it to you. So nominal shear strength, we know that V equal to Vu divided by Bd. We know the value of Vu and Bd. So I have calculated the value. I am getting it as 1.08 Newton per mm square. Next I am going to calculate the shear strength of concrete tau c. It will be calculated based on the percentage of steel. So Pt equal to Ast divided by Bd into 100. So here AST means we need to use the number of bars, 8 into pi into 25 square divided by 4 divided by B, that is 300, into D is 500 into 100. So the percentage of reinforcement we are getting is, so the value which I am getting is 2.62. So based on the code book, we know that in page number 73 we will have a table. So from this table we need to calculate the value of tau v. So here we are getting it as 2.6. So here if you see, we are having the range of, that is 2.5 and 2.75 for M20. So here if you see 2.5 also 0.82 and 2.75 also 0.82. So I am going to directly take it as tau c equal to 0.82 Newton per mm square. So here since tau v is greater than tau c, we need to provide shear reinforcement. Therefore, shear reinforcement is needed. So how to provide this shear reinforcement? So here shear reinforcement is needed. So how to provide this is given in our code book itself. In page number 73, if you look at this table, shear reinforcement shall be provided to carry a shear equal to Vu minus tau c into Bd. So here Vu minus tau c into B into D. So here if you see, Vu is 162.4 into 10 to the power 3, because since we are tau c into is calculated in terms of Newton per mm square. So I am converting the Vu, that is which was given in kilonewton, as Newton, minus tau c is 0.82 and B is 300 and D is 500. So which will give the balance here. This step is nothing but it is called as balance shear, which need to be supported by the reinforcement. So we need to calculate this balance shear, because this balance shear means the shear which is exceeding the limit of concrete. So concrete can carry a certain shear and the remaining balance shear need to be carried by using the stirrups. So here we are getting the value as, the balance shear will be written as VUS. It is equal to 162.4 into 10 to the power 3, and if you calculate this value, we are getting it as 123,000. So the balance shear is 39.4 kilonewton. So here if you see, for using vertical stirrups, for providing vertical stirrups, we need to use this formula. So I am going to assume, assume two-legged 8 mm dia bar as vertical stirrups. So what I am going to use two-legged 8 mm dia bar as vertical stirrups. So here if you see this formula, we are having it as VUS equal to 0.87 Fy ASV D divided by SV. This SV is the only thing which we are going to calculate. Here ASV is nothing but area of shear reinforcement. We have assumed that we are going to provide two-legged of 8 mm dia bar as vertical stirrups. So to calculate ASV, we are going to provide two legs. So 2 into area of the bar is pi into 8 square divided by 4. So if you calculate this, we will get the value. ASV, that is area of shear reinforcement, is 100.53 mm square. So I am going to calculate the SV. So I am going to calculate the SV value. So sorry, here it is 8. So I am going to calculate the SV value. So here if you see, I have calculated my value. So VUS is nothing but 39.4 into 10 to the power 3 equal to 0.87. Fy is 415 into ASV, which I have calculated, is 100.53 into depth of the beam is 500 mm, effective depth is 500 mm, divided by SV, that is spacing. So I am calculating SV equal to, I am going to bring this value here, So the spacing which I am getting is 460.6 mm. But as per our IS 456, the depth cannot, that is the spacing cannot exceed 300 mm. So therefore provide two-legged 8 mm dia stirrups at 300 mm center to center spacing. So with this, the problem come to a closure. So next we are going to see about a L beam, which we will see it in the next class. Thank you.